We mention these as frequencies that you may, not saying you will, but you may see them on the cables leading to the motors. Okay, the motors themselves are very low noise. Okay, outside of the case of the motor, if you're just to measure RF around this motor, you're not going to get much of anything. But you know what? You hook a cable to it, the cable's like an antenna. Okay? Our motor may be made to CE and UL specs, and CE specs about noise emissions, but it meets the CE directive for industrial applications. We did not meet the CE directive for super clean biomedical applications. Okay? That's not our market. But have we been used in biomedical? Yes. We're on CAT scans, MRI machines, ultrasound machines. We're on them all the time. But it's not our job to spec CE or noise emissions for the entire machine. That's the job of the customer integrator. Okay? So it can meet that spec just fine. So what we do is we put this out there so people understand that they may see some harmonics. How do they get rid of that? They can use a cable that's shielded, which we sell, or they can additionally add ferrite bead clamshell noise suppressors on it, which take out the large spikes that come on the on-off switching points. Okay, just like I mentioned earlier, where you open up the switch and the voltage goes up and back down, it also happens inside cables with regards to PWM signals, on and off, or binary transmission signals. The same exact thing happens in a cable. The higher the inductance of the cable, the more the noise transmission. A high inductance cable will get these spikes as magnetic fluxes change between the shield and the conductor within the cable. That's why you put ferrite clamshell things on cables such as monitors. If you've ever seen these things, well, I don't know where the other end of it is, somewhere down here, you'll see that big fat thing on there. It's an iron ferrite bead to try to suppress these noise spikes. That's what that's from. Okay? You'll see 32 megahertz process clock speed, PWM is 16K. That is audible, very high pitch, but it's audible. 140K plus or minus 10% mode dependent. Our regulator regulates frequency to regulate power required by the CPU, so that's a little bit floating. Drive stage 100 megahertz, chances are you'll never hear it, never see it, because it's way up there. 8K hertz adjustable, that's software. That's the rate internally on the circuit board. Chances are you would not see this. However, you can see the effect that it drives back to the drive stage on how fast you see an oscillation within the motor winding. Okay? It will affect it audibly, but typically not electrically like you would see on a cable. Okay? We have text-based programming, 32K of data and storage. We already talked about that. You'll learn more about subroutines. We can have up to 1,000 subroutines. Stack pointers, 10 nested go stubs. You'll learn more about that later. I don't want to explain that now. We already mentioned the baud rates. There is one thing I'll mention on here. I think Chuck's talking about buses later, but you have all sorts of baud rates you can set on CANopen and DeviceNet. The reason you may have to do that is because of electrical noise in the system. You may want to change the baud rate to get away from electrical noise harmonics, so one piece of equipment doesn't interfere with the communications of another. Okay? Any other questions so far? Yes, no, maybe?